everyone. My name is Juan Silveira. I'm a software engineer in the DeepMind health team. And I'm here to tell you a little bit about DeepMind and the work that we've been doing. So let me start by telling you who we are. So DeepMind is a British artificial intelligence company that was founded in 2010 and joined forces with Google in 2014. And we're a bit of an unusual company in that we have a two-part mission. The first part of that mission is to create general artificial intelligence. But what do we mean by general artificial intelligence? And the key here is being able to create agents, algorithms that can work and do well in a variety of tasks and environments. And the key to that is to get them to learn from their own experience. So not to pre-program them with behaviors, but to actually allow them to learn from what they can see in their environment. So that's the first part of our mission. But we also have a second part, which is to use artificial general intelligence to address pressing social challenges. So we recognize the potential of AGI to really make a change in the world, and we want to make sure that the benefits of that reach everyone, and that we can use it to address things that we all as a society have to deal with. So how are we doing that? So there's our mission, how we actually formed. We're at heart a research organization. We're based in London, in King's Cross, and we have more than 300 of the best AI research scientists in the world, all here in Europe. We, like any research organization, we do our research in the open. So we actually publish over 100 papers in different research organizations. And we joined forces with Google in 2014, which means that we could really take our speed to the next level. And the mixture of these two things means that we're a bit of a hybrid organization. On the one hand, we have the very, very long-term focus of academia, because AGI is not something that's going to happen anytime soon. But we're very, very focused on making that happen. But at the same time, we have the pace, the scale, and the agility of a very well-funded startup. And because of the second part of our mission, we also have a lot of people in our organization that have the kind of social impact values that you only find generally in the public sector. Now, I talked about AGI, artificial general intelligence. How is it that we're trying to resolve this? And we're trying to resolve this by building general purpose learning systems. And this, just to give you an idea, involves creating agents that interact with an environment. So these agents get signals and make observations of the environment and decide on actions to take that then get reflected in that environment. And once they've taken those actions, they can actually observe again how that affects the environment. But the key thing is that they have a goal, so a function that tells them whether they're closer to actually achieving what it is that they're trying to do. And this whole process is called deep reinforcement learning. I'm sure some of you have heard about it, and it's key to what we're doing at DeepMind. The environment that we use for this is key, and we've actually had quite a bit of success using the old Atari games as a testbed, as an environment in which to train agents. So we've taken over 100 of the classic Atari games, so this includes things like Pong, Frogger, Montezuma's Revenge, Breakout, some games that I'm sure many of you have played. And we've created an environment in which what the agent sees, the inputs, are just the pixels on the screen. So it just gets that matrix of pixels for RGB values, that is what you would see on the screen. And the outputs are the controllers in the Atari game, which are very simple controls. So you could go up, down, left, right, and a trigger button. But the really important thing is that the agent is not told what to do. So it's not told the rules of the different games. It's not told like how it works, like what the internal functioning of the Atari game. So any knowledge needs to be learned from scratch with zero pre-programming, like no strategies for how to play with different games. what we give it is like the goal, and that is to maximize the score. But the key thing that I think is fantastic when I first learned about this was that one agent plays all of the games. So you don't train one agent for each game, you train one agent in all of the games and have it play all of the games. So a good analogy of how this works is that you could have a little robot in an arcade sitting in front of the game, looking at the screen and moving the controller, and that's all. It doesn't have any knowledge of the internals of how it works. So let me show you how this looks like as the agent is being trained and how it evolves. So this is the game of Breakouts. I'm sure many of you have played. How many of you have played Breakout before? Great, I won't explain it then. So the agent starts training after half an hour. It doesn't really know what's happening, so it just loses quite quickly. Sometimes it manages to bounce the ball back, but mostly just loses quite quickly. After an hour of training, gets a little bit better. It's like maybe survives 2 bounces, but that's about it. It actually still loses quite quickly. But after 2 hours, it's now doing how you would do probably if you start playing Breakout right now. So it's like runs around, bounces the ball back, and manages like a basic level of competence. But the great thing is what happened unexpectedly after we let it play for 4 hours, and the agent started doing this. So for those of you that have actually played Breakouts for some time, you know that this is the winning strategy. It's like you break the sides and you push the ball at the top, and it just does the work for you. But this is not something that was pre-programmed on the system. It's not something that we told the agent about. It's something that the agent discovered by playing the game thousands and thousands of times with this goal function of improving the score. And this is the power of deep reinforcement learning that allows these kind of behaviors to emerge. So we used the Atari games for a long time for research, and we still use them today. And we published papers about this research, and it was quite successful. But a few years ago, there's a team on DeepMind that started looking for a new challenge. And that challenge was the game of Go. Let's see if I can get So for those of you that don't know Go, it's a very ancient game originated in China about 3,000 years ago. And it's considered by many to be more than just a game. People think about it as a spiritual dimension, as poetry or art. And it was considered to be one of the 4 arts that were key to be mastered by a true scholar. It is hugely popular in many places, especially in Asia. There's 40 million players, 2,000 professional players, and there's Go schools throughout Japan, South Korea, and China. And the thing about Go, why it's a great challenge, is because it has very simple rules. You could learn the rules of Go in a couple of minutes. But from those rules actually arises a huge, profound complexity. So to give you an idea of the scale, there's an estimate that there's about 10 to the 80 number of atoms in the universe, but there are 10 to the 170 possible board configurations in Go. So it's impossible to play Go by brute forcing or by trying to explore all of that possibility space with no good strategy. And that means that Go has been one of the great challenges for AI, because no computer program could beat a human professional Go player. If you compare this to chess, which is something that computer programs have been doing very well for a while, the branching factor, the number of possible moves at any given time in chess is 20, and in Go it's 200. So a team in DeepMind started creating an artificial intelligence program that's called AlphaGo. And AlphaGo is actually composed of 2 neural networks. So you have the policy network and the value network. And the policy network was initially trained using human games. So we took thousands of games from an online Go server that we had access to and trained this network by watching those games, and then trained it further, but playing against itself. And the objective of the policy network is to, given a particular position, a particular configuration of the board, to say which positions are most likely to be played next. And that allows you to narrow down that branching factor. The other network, the value network, takes the configuration of the board, and what it tries to estimate is how likely is white or black to win. So instead of having to actually play out the entirety of the game to try to figure out who's most likely to win, this allows us to cut down how deep you need to go in order to explore the possibilities of the game. So the combination of these two networks is what made AlphaGo so powerful. But let me tell you a little bit how sort of the progression of this went. After creating this network and training it, the AlphaGo team actually managed to get a 100% success rate against the best computer programs. But we know that they were not as strong as even the level 1 professional Go players. So we got a professional Go player, Van Hooy, who is the 3-time European Go champion and a 2-dan professional player. And he came to the DeepMind office to play a 5-game match against AlphaGo. And AlphaGo actually won 5-0, which was completely unexpected because it was the first time a computer program could beat a professional player. And after that, we wanted to see how much further it could actually go. So we managed to schedule a match in Korea, in Seoul, against Lee Sedol. And Lee Sedol, for those that don't know Go, is actually a legend in the world of Go. He has won more international competitions than I think only one other person, and is considered by many to be the best Go player of the last decade. So the AlphaGo team went to Korea, played on this match, which was like a huge event. It was everywhere on the newspapers, on the TV. It was watched by more people that actually watched the Super Bowl in the US. And the fantastic thing to me about these matches, once again, 5 matches, it's not just that, like the end result, but the fact that on the second game, AlphaGo made a move 37, that had a 1 in 10,000 chance of being played according to the policy network. So it was a very, very super unlikely move. Took the commentators by surprise. Many thought it was actually a mistake, but actually turned the game. And it was Van Hooy, commenting on that game, said that it was actually a beautiful move. And then in game 4, the same thing happened, but Lee Sedol made a move once again that AlphaGo didn't expect, because the policy network would say they had a 1 in 10,000 chance of being played. And people were talking about that move as the touch of God, a beautiful, beautiful move again. So the fantastic thing about these matches, to me, it's not so much the result, but the fact that the computer and the human professional Go player playing together actually reached new levels of play and could actually come out with these beautiful games by playing together. After this, we actually had a further Go Summit, the Future of Go Summit, precisely to explore this, to explore how AlphaGo and human players could play together to bring the art of Go to the next level. So both our work with Atari and our work with AlphaGo was done in the open, like I mentioned. So we published papers for both of these and many other things. We were very lucky that these 2 papers actually got onto the cover of Nature, which within 18 months, it was the first time for an artificial intelligence research organization. And let me tell you about some of the things that we've done since then. So these are 2 projects that I think I'm particularly excited about. So one of them was lip reading sentences, in which, once again, we managed to push the boundary from being able to recognize particular words, like a limited vocabulary, to just being able to recognize and have good results on unbounded natural language, so being able to recognize any speech. And there's also WaveNet. So WaveNet, if you never heard about it, I really encourage you to go and see the blog post, the DeepMind website, where you can actually hear samples that were generated by WaveNet and how they're incredibly natural. It really changed the way that we do text-to-speech, because up to now, text-to-speech was done by taking recordings of a professional actor of particular sounds and then putting them back together to form a phrase. But WaveNet actually generates, if you know about how digital audio is encoded, it's 16,000 samples per second. And what WaveNet does, the neural network does, is generates each of those samples at a particular step. So it actually generates the audio wave. And the amazing thing is that I managed to cut the gap between the best text-to-speech systems available and a human voice by 50%. So we're halfway closer to reaching the level of a human speaking, generating natural speech. And the great thing about this is that I think it really shows how this kind of algorithms, how reinforcement learning can be adapted to new environments, new domains really easily because they are more generic, because they're a step closer to general intelligence. So that is the work that our research arm has been doing. But let me tell you also about how we're applying this. So this is a photo of a Google data center. And in particular, it's the cooling area of the Google data center. The very colorful pipes are actually coded for different water flows to different areas. So as you can imagine, a Google data center is already a very, very optimized data center. It's some of the most efficient data centers in the industry. And after DeepMind joined forces with Google, it was natural to start working with some of the Google teams. So a team from DeepMind started working with the Google data center team to create an agent that had as inputs the sensor readings from the data center. So things like the temperature, the weather outside, the pressure in the cooling system, how much power is being drawn by the servers. And the output was the configuration parameters for the cooling system, things like the water flow pressure or the fan pressure. And the result of this, of applying this agent to this very optimized data center, was a 15% improved overall efficiency over the entire data center, which was it's a fantastic improvement in a system that's already been heavily optimized. So we think this shows how AI can be applied to real-world problems, for example, to reduce energy usage and reduce carbon emissions. The other applied project that I'd like to tell you about is DeepMind Health. DeepMind Health is a project I work on. And it was launched in February 2016 as our first external-facing applied project. And we're really excited about health because we're excited about the potential for digital technology combined with better data to support clinicians in transforming the way they do patient care. We've grown, and we're now a team of 70 clinicians and engineers and designers. But as we started to go into the health space, the first thing we did is we spent time on wards in hospitals. And we realized how much was needed still to be done to deliver sort of the dream of the paperless hospital. So things like pagers or paper or pen are still very much part of the day-to-day life for nurses and doctors. And you can contrast this with what your day-to-day life is like. So because of the services that all of us create, you have the information that you need when you need it at any time in your pocket. So the first step towards delivering AI-enabled technology is to make sure that the doctors and nurses have the latest digital tools. So we created this project called Streams. And Streams is a mobile app that doesn't have artificial intelligence built in. And what we aim to do with it is to support clinicians in their existing workflows by, for example, sending alerts to a specialist when we detect that a patient is deteriorating, and then making sure that they have access to the relevant information when they need it. So the idea here is to help clinicians get patients from their tests to their treatment in a matter of minutes instead of hours. And at the same time, in parallel to this, we're also using artificial intelligence to help with cutting-edge medical research. And there's a couple of projects that we're working on here one of them with the Moorfields Eye Hospital, in which we're working on retinal scans that can detect diabetes-related or macular degeneration. And the thing about this area, why it's so exciting to be working on this, is even though there's a 25, if you have diabetes, 25 times more likely to suffer sight loss, 98% of the sight loss is preventable if it's detected early enough. And we hope that we can help with that detection. We're also working with the University College London Hospital on radiotherapy planning for head and neck cancers. So head and neck cancer treatment are very tricky, because there's a lot of things going on there, and the treatment needs to be planned very, very accurately. That means that in order to treat one patient, a radiotherapist needs to spend about 4 hours to plan each of the treatments. And there's already a huge shortage of radiotherapists in the UK. So we hope that we can reduce this from a very, very lengthy task to a much shorter verification task. We have a lot more information about this in our website, deepmind.com/health. And if you have any questions about all this, you can send us an email at sayhi@deepmindhealth.com. And that's all I had for today. If you have any questions about this and you want to talk about any of that, find me after the talk, send me a message. And if you're interested in what we're doing, also check out our website at deepmind.com/careers. Thank you.